Hello everyone, I'm Sreedhar. The title of my thesis is Inter-Numerology and Inter-Carrier Interference in Mixed-Numerology OFDM systems. So this is the outline of my talk. First, I'll introduce what is Mixed-Numerology in 5G in radio. Then I'll discuss the two key challenges in Mixed-Numerology OFDM systems, which are Inter-Numerology interference, abbreviated as INI, and Inter-Carrier interference, abbreviated as ICI. In this, I will discuss the main reason for these two issues, which is the loss of orthogonality of the subcarriers. Then I'll discuss the factors affecting INI and ICI. Next, we'll focus on iso-OFDM systems. Here we shall see the analysis of INI and ICI. Also, we shall see a mitigation technique, which is the subcarrier power allocation. Next, we'll move to MIMO-OFDM systems. Here we shall see the analysis of INI and ICI, and also a mitigation technique, which is the precoder design and eigenmode power allocation. Then I'll give my conclusions. So coming to mixed numerology OFDM. So in 5G, the entire system bandwidth is divided into bandwidth parts. These are non-overlapping, and each bandwidth part can be assigned an OFDM waveform with distinct parameters. The parameters are subcarrier spacing and cyclic prefix, and these two parameters constitute a numerology. Here I am showing a mixed numerology OFDM system with two numerologies. Figure on the left shows the frequency domain view, and the figure on the right shows the time domain view. Here, as you can see, the subcarriers shown in the green color, they belong to bandwidth part 1. And the subcarriers which are shown in orange color, they belong to bandwidth part 2. You can notice that the subcarriers belonging to different bandwidth parts, they use different parameters. For example, the subcarriers in bandwidth part 1, they use 15 kHz subcarrier spacing and a cyclic prefix duration of 4.76 microseconds. Whereas the subcarriers in bandwidth part 2, they use a subcarrier spacing of 30 kHz and a cyclic prefix duration of 2.38 microseconds. So in 5G, there are total 7 numerologies defined by 3GPP. The subcarrier spacing and cyclic prefix duration for each numerology are shown in this table. The first 3 numerologies are used in the FR1 band, which is the sub-6 GHz band, and the last 4 numerologies are used in the millimeter wave frequencies as well as sub-terahertz frequencies. This is in contrast with LTE, where only the 15 kHz subcarrier spacing is the only available numerology in LTE. As you can see here, the subcarrier spacing increases from 15 kHz to all the way to 960 kHz, and the cyclic prefix duration proportionally reduces from 4.76 microsecond to 0.075 microsecond. So here I am showing the resource grid representation for the mixed numerology. Once again, I am showing a system with two numerologies. So each rectangle of this resource grid is called a resource element. This can convey one information symbol. As you can see here, the resource elements which are shown in the green color, they are longer in time and they're shorter in the frequency axis because they use a smaller subcarrier spacing. Whereas the resource elements shown in orange color, they are shorter in time and longer in the frequency axis because they use a larger subcarrier spacing. Now let us see the need for mixed numerology. The first reason is the diverse requirement of use cases. In 5G, there are 3 use cases: EMBB, which stands for Enhanced Mobile Broadband; MMTC, which stands for Massive Machine Type Communication; and URLLC, which stands for Ultra Reliable Low Latency Communication. So these use cases have diverse use requirements. For example, URLLC needs a very low latency. So here we need to use an OFDM waveform with a shorter OFDM symbol duration. On the other hand, MMTC needs more robustness towards delay speed. So here we need to use an OFDM waveform with a longer cyclic prefix duration. So these requirements can't be satisfied by a single OFDM waveform. So this is one of the motivation factors for using multiple numerology. The second reason is the wide range of operating carrier frequencies. In 5G, the carrier frequencies can go from the sub 6 gigahertz to the millimeter wave frequencies and also the recent subcarrier frequencies. So at high carrier frequencies, phase noise is a dominant impairment. So to handle the phase noise at high carrier frequencies, we need to use an OFDM waveform with a shorter symbol duration. Third reason is to limit the FFT size. So in 5G, the bandwidth can go as high as 400 megahertz. So to accommodate this large bandwidth and keep the FFT size under control, we need to use an OFDM waveform with a larger subcarrier. Now coming to the main challenges in Mixed-Numerology OFDM. The first one is the Inter-Numerology interference. So the resource elements of numerology 2 can interfere with the resource elements of numerology 1 and vice versa. So this is called Inter-Numerology interference. And also the resource elements within a single numerology can interfere among each other under certain conditions. I'll explain the conditions later. So this is termed as inter-carrier interference. So these two are the critical challenges in Mixed-Numerology systems. Also, they need to be mitigated jointly. So primary reason for these two interferences is the loss of orthogonality of subcarriers. So to understand the reason behind this, let us see the orthogonality of subcarriers in OFDM. So in OFDM, the complex exponentials are the subcarriers. So here I'm showing only the real part for simplicity. So the transmit subcarriers are denoted by the functions g of t. They have a cyclic extension, whereas the receive subcarriers, they are zero within the cyclic duration. At the receiver, an inner product is performed between the transmit and receive subcarriers. And whenever both the subcarriers belong to the same frequency, their inner product is 1, otherwise their inner product is 0. So they are orthogonal. So here I am showing the product of the transmit subcarrier and the complex conjugate of the receive subcarrier. As you can see, it has an integer number of cycles within the OFDM simulation. So the area is 0. This can also be seen from the frequency domain representation. At the frequency 0, the value of the Fourier transform is 0. So these two subcarriers are orthogonal. Now let us see the case where there is a frequency offset. Now, because of this frequency offset, the transmit subcarrier does not have integer cycles within the OFDM symbol duration. And due to this, the product signal also does not contain integer cycles within the OFDM symbol duration. So the area under this curve will be non-zero, and these two subcarriers, they will lose their orthogonality. This can also be seen from the frequency domain representation. Due to the frequency offset, the sinc function has been shifted from its original position, and now at the frequency 0, the value of the Fourier transform is non-zero. So these two subcarriers are not orthogonal. This is due to intercarrier interference. So notice that ICI arises even in single numerology OFDM, and it is well studied in the literature. Now let us see the inter-numerology interference. So here we'll consider two numerologies. So as a convention throughout this talk, we'll assume that numerology 1 uses a smaller subcarrier spacing and numerology 2 uses a larger subcarrier spacing. First, let us see the INI at numerology 1 receiver. So here the receive subcarriers are longer, and the transmit subcarriers are shorter. As you can see in the figure of the plot product of the signal, there are no non-integer cycles within the OFDM symbol duration. So these two subcarriers are not orthogonal. Once again, when you consider the numerology 2 receiver, here the receive subcarriers will be shorter and the transmit subcarriers will be longer. Once again, you can see that within the interval of integration, the sinusoid does not have integer cycles. So these two subcarriers are not orthogonal, and they cause this is the inter-numerology interference. So now we have seen the INI and ICI in a very simplified scenario. In practical deployment, these are impacted by the wireless channel propagation as well as the hardware impairments. So now let us see the factors which affect INI and ICI. So the first factor is the wideband time varying channel. So it is denoted as the set of fading process corresponding to each delay. Now, a popular model for wireless channel characterization is the WSS-US model, which stands for wide sense stationary and uncorrelated scattering. As per this model, the fading process corresponding to each delay is wide sense stationary, and the fading coefficients corresponding to distinct delays are uncorrelated. Now, the time variations are captured by the temporal autocorrelation, which is denoted by RL of W. So, it is the expectation of the fading coefficients of the L path, which are separated by a delay of W sample. Now, in 3GPP, the JX model is employed to characterize the temporal autocorrelation. As per this model, the temporal autocorrelation takes the form of a zeroth order Bessel's function of the first kind. Now, the delay characterization of the wireless channel is given by the power delay profile. So, it is a value of the temporal autocorrelation of the alpha at lag 0. So, when this is seen as a function of L, so this gives the power delay profile. An example power delay profile, which is employed in 5G, is shown here. This is the tapped delay line channel model. So, here there are 24 paths. These are the normalized delays for these paths. And the relative powers of these paths are shown in this column. And the fading distribution for each path is the Rayleigh distribution. So this is only the SISO characterization. The MIMO characterization I'll explain later. So the next factor which influences INI and ICI is phase noise. So phase noise is the random disturbance in the phase of practical oscillators. So there are two models available to model phase noise in literature. The first one is the filtered Gaussian process model. It is typically applicable for phase locked loop based oscillators. So in this model, phase noise is generated by passing a wide Gaussian noise through a filter with a desired transfer function. And the transfer function of this filter dictates the power spectrum of the phase noise. In this figure, I am showing an example power spectral density of phase noise at multiple carrier frequencies. As you can see here, as the carrier frequency increases, the phase noise level increases. The second model is the Wiener model. This is typically applicable for free running oscillators. So, as per this, in this model, the phase noise is modeled using a random walk based process. The successive phase increments, they are modeled using a zero min Gaussian IID process. And the variance of this Gaussian random variable is given by 4 pi omega t, where omega is the one-sided 3 dB bandwidth of the oscillator power spectral density, and t is the sampling time. So now we focus on SISO OFDM systems. We quantify the ICI power as well as INA power at each subcarrier for the users. And we'll also develop some insights for the dependence of ICI and INA on the system parameters. So first, let us focus on ICI. So here, we're considering a OFDM transmitter and OFDM receiver, single antennas. So this is the resource grid for the OFDM transmitter. So out of the N subcarriers, we're using Z subcarriers. Subcarriers start at offset O. So in the OFDM modulator, an endpoint IFFT is computed and the cyclic prefix is added. The analog and RF modules, they induce a transmit phase noise. So the signal transmitted is received at the receiver via the time varying wireless channel. And at the RF processing modules at the receiver, a phase noise is induced. Further, after down conversion at the baseband, the cyclic prefix is removed and an endpoint FFT is computed. The output of the FFT contains the estimate of the transmitted information symbols. So this contains the desired signal component as well as ICA component in addition to AWG noise. So now we are interested to quantify the ICA power at each subcarrier. So this is the received signal model. So this linear convolution is due to the effect of wireless channel propagation, and the complex exponential is due to the phase noise. So here phi of n is the effective phase noise, which is the sum of the transmit phase noise and receive phase noise. So this is our first result, which quantifies the average ICI power at any subcarrier K. So this is the expression for the average ICI power. So notice that it depends on the subcarrier offset O. There is a summation over all the subcarriers, excluding the subcarrier K. There is a summation over the time index W, and also there is a summation over the channel tap index L. You can see that it depends on the phase noise autocorrelation and also on the temporal channel autocorrelation. So this is the bandwidth average ICI power, which is the linear average of the average ICI powers at all the subcarriers. So the expression for this bandwidth average ICI power is shown. So these two expressions for average ICI power and bandwidth average ICI power, they do not directly reveal the dependence on the system parameters. So to gain further insights, we will derive bounds for this bandwidth average ICI power. And these bounds will reveal the dependence on the system parameters. So to derive the bound, we'll use the composite channel, which is the product of the phase noise and the channel fading coefficient. So for this, we'll introduce the composite autocorrelation, RL bar of tau, is shown here. So in the power spectrum for the composite autocorrelation is given by SL of F, which is nothing but the Fourier transform of the composite autocorrelation. We'll introduce two moments for this composite autocorrelation, the second moment and the fourth moment. So these two moments can be computed in closed form. For example, when phase noise has a uniform power spectrum and the channel has a Doppler power spectrum, JX Doppler spectrum, the moments can be computed in closed form as shown here. So notice that the second moment depends on the quadratic terms of the system parameters, whereas the fourth moment contains both the fourth power terms as well as the quadratic terms of the system parameters. So our work generalizes the approaches by Lee and Shimini and also Kai and Giannakis. So these works have used the continuous time formulation for the OFDM signal, and also they have assumed infinite number of subcarriers, and also they have not considered phase noise in their system model. So our work generalizes the works of Lee and Shimini and Kai and Giannakis. So these are the bounds which we have derived for the bandwidth average ICI power. This is the upper bound and this is the lower bound. These two bounds differ in the third term. Notice the presence of the second moment and the fourth moment. So in our numerical computations, we have seen that the coefficients corresponding to the fourth moment are relatively small in magnitude when compared to the coefficients of the second moment. So the quadratic dependence is more dominant in these bounds. So in this plot, we benchmark the bounds which we have derived for the bandwidth average ICI power. So here we are plotting the normalized bandwidth average ICI power along with the bounds as a function of the scaled Doppler spread. The black curve shows the exact ICI power. The red star marker shows the upper bound, and the green circle marker shows the lower bound. As you can see, both the bounds which we have derived are very tight. Here we are also showing the upper and lower bounds of Lee and Shimini. Upper bound is shown by the triangle marker, and the lower bound is shown by the dashed curve. So one interesting observation is that the continuous time formulation can be slightly misleading result because, as you can see, the lower bound is greater than the exact ICI power. We are also showing the universal bound 1 of Chi and Giannakis. So notice that this bound is quite loose compared to other bounds because this is a universal bound. So it can be applied to any Doppler spectrum. It need not be restricted to the JX Doppler. So in this plot, we have ignored phase noise because the benchmark schemes are available only for the case when that's known. So now we'll focus on inter-numerology interference. So we'll focus on the downlink setting where the base station is serving two users. The users use different numerologies, and the subcarrier spacing of user 2 is 2 power mu times the subcarrier spacing of user 1. So our model can be easily generalized to k users because the information symbols different users are independent. The total INI power at a user will be the sum of the INI powers from all the interfering users. So generalization to arbitrary users is straightforward, and this we have incorporated in our thesis. So this is the transmit signal model. The transmit signal is the sum of the signals for user 1 and user 2, and the power of each user signal is denoted by Pk. Now the power can be expressed in terms of the energy per resource element divided as EPRE. The relation between power and EPRE is shown in this equation. So when a user uses Zk subcarriers, the total energy will be EPK into Zk, and each resource element occupies Nk samples. So the power will be the ratio of EPK into Zk and Nk. So EPRE is a very critical parameter in OFDM systems. SNR also is specified in terms of using EPRE. It will be the ratio of signal EPRE and noise EPRE. And the EPRE ratio of two users, which is denoted by this parameter beta, is shown here, which is the ratio of the EPREs of the users. So in 5G, it has a very large dynamic range, minus 32 dB to plus 32 dB. So when the EPRE ratio is very high, user 1 will receive high amount of interference from user 2 because signal power of user 2 will be very high. Similarly, when EPRE ratio is very low, user 2 will receive high amount of interference from user 1. So this is our model for the ISO OFDM case for the downlink. The base station is serving two users. The signals corresponding to the two users are generated in the base station. So these are the resource grids for the two users. So notice resource grids are dimensioned differently. User 1 uses Z1 subcarriers and user 2 uses Z2 subcarriers. The offset for user 1 is O1 and the offset for user 2 is O2. For user 1, an N1 point IFFT is computed. And for user 2, N2 point IFFT is computed. And the baseband signals are added in the time domain and are processed by the analog and RF processing modules, which induce transmit response. The signal transmitted by the base station is received at both the users via their respective wireless channels. The RF subsystems at each user, they induce phase noise, and at the baseband, the respective cyclic prefix is removed and FFT is computed. So the output of the FFT at each user will give the estimate of the transmitted information symbols. So these estimates contain the desired signal component as well as INI and ICI component, in addition to AWE noise. So the ICI analysis of ICI component we have already seen earlier. Now we'll focus on the INI component. So we are interested in computing the power of the INI component at all the subcarriers for both the users. So this is our result related to INI, which shows the average INI power at subcarrier P of user 1. This is quite a lengthy expression. The key takeaways are that the INI power depends on the EPRE of the interfering user. It has a summation over the subcarriers of the interfering user. And there is also a summation over the channel tab. Notice that it depends on the phase noise autocorrelation and also on the temporal autocorrelation of the channel. And one critical parameter which affects the average INI power is the parameter spectral distance. So this spectral distance is the distance between the interfering and victim subcarriers of the users, but this distance is measured in the scale of the lower subcarrier spacing inequality. So here O1 plus P will be the index of victim subcarrier, and O2 plus U will be the index of interfering subcarrier. And the subcarrier index is mapped to the scale of lower subcarrier spacing numerology. the index will be modified shown here. And the difference between these two terms will be the spectral distance. So this result shows the average INI power subcarrier P of the user 2, which is the higher subcarrier spacing user. So once again, you can see it depends on the EPRE, also depends on the subcarrier allocation. So, and also it depends on the spectral distance. This expression is different from the INI power at user 1 because there is no summation over the channel tags. So it does not depend on the power delay profile. So because this is the normalized temporal autocorrelation, so this INI power does not have any dependence on the power delay profile. Now, on the lines of ICI, we have also derived bandwidth average INI power and the bounds for it. And also we have established the quadratic dependence on the system parameters. I'm skipping the details here. So now we validate the expressions which we have derived for the NA power for both the users. So this is the allocation of subcarrier allocation for the users. So both the users use 12 subcarriers. The offset of user 1 is 60 and the offset of user 2 is 40. So here there is some guard band. In the absence of guard band, the offset for user 2 will be 36. The EPRE ratio is 3 dB. And the subcarrier spacings of user 1 are 15 kHz and user 2 is 30 kHz. So here we are plotting the normalized average INI power as a function of the subcarrier index for both the users. So the blue curve shows the result for without guard band and the red curve shows the result for band. So the key observation is that INI power is different across subcarriers for both the users and it has a dynamic range of around 24 dB. And the INI power is oscillatory at user 1, whereas it is monotonic at user 2. And also we can see that the introduction of guard band reduces the INI power. So guard band is one technique which can mitigate the INI power, but the disadvantage is that we lose on spectral efficiency. So later we'll focus on mitigation techniques other than guard band to alleviate INI. So in this plot, we are showing the bandwidth average INI power and bounds. Figure on the left shows the result for user 1 and the figure on the right shows the result for user 2. Here we are plotting the normalized bandwidth average INI power as a function of the scaled phase noise bandwidth. So as you can see, both the bounds are tight and they match the quadratic dependence. And one key observation is that there is no much variation in the bandwidth average INI power with increase in the phase noise bandwidth. So now that we have quantified the ICI and INI powers at both the users as a function of the subcarrier index, and we have seen that the INI and ICI powers are different for different subcarriers. We'll exploit this fact to mitigate jointly INI and ICI. Our goal is to allocate powers to subcarriers to minimize the block error rate. So we'll frame an optimization problem. So the objective function we'll choose is the upper bound of the block error rate. So first here we'll consider the uncoded case. First, for the coded case, the characterization of BLER in closed form is intractable. So we'll consider the uncoded case. And for the uncoded case, we'll use the upper bound for the objective function. So this is the sum of the average symbol error probabilities over the subcarrier indices. So this can be obtained by using the union bound on the uncoded blocker rate. So the optimization variables are subcarrier powers. Here we have a total power constraint and also non-negativity constraint because the optimization variables are powers. So this is a convex optimization problem and we have derived a closed form solution for it. The solution for this problem is shown here. Because of its mathematical form, we have named it as statistical square root power allocation. So notice that it is different from water filling because the objective function is not the sum rate of the subcarriers, And also we do not use the instantaneous channel gains, the objective function. The optimal solution depends on the parameter AP of K, which is the sum of INI and ICI powers at subcarrier P in addition to the diffusion noise. It is scaled by a parameter C2. This parameter C2 depends on the modulation scheme which we use. So this lambda parameter in the optimal solution can be found numerically by substituting the optimal powers in the total power constraint and solving this equation numerically. We can find the parameter lambda. So now we'll compare our proposed power allocation with the uniform power allocation which is available by G. So this is a allocation of the subcarriers to the users. So user 1 uses 12 subcarriers and user 2 uses 84 subcarriers. So the offset of user 1 is 6 and the offset of user 2 is 172. So as you can see here, the SSRPA deviates significantly from the uniform power allocation. And also we can see the oscillatory nature for the power allocation for user 1 and the monotonic nature for the power allocation for the user 2. This is because of the oscillatory nature of the INI powers at user 1. So one more key point to observe here is that for user 1, the subcarriers towards the left are assigned higher powers. And for user 2, the subcarriers towards the right are assigned higher. Now, these subcarrier indices of user 2, because of the DFT wraparound, they can be mapped to -84 to -1. So effectively, the subcarrier 255 is closer to user 1. So this experiences higher INA power. Thus, it is assigned higher power to the subcarrier. So effectively, our proposed power allocation scheme assigns more power to the subcarriers which face higher INA power. So now we'll compare the performance of our proposed power allocation scheme with the uniform power allocation in terms of blocker rate. So the figure on the left shows the results for QPSK and 64 QAM. And the figure on the right shows the results for 16 QAM and 26 QAM. So the lower order modulation schemes use a higher EPRE ratio, whereas the higher order modulations they use a lower EPRE ratio. So as you can see, after the SNR of 30 dB, the reduction in the blocker rate by our proposed power allocation is quite significant. Now we shall see the results for the coded case. Here we are plotting the blocker rate as a function of SNR, both the power allocation schemes. So here we are using the 64 QAM MCS of 5G, which uses a code rate of 948 by 1024 using LDPC code. As you can see here, our proposed power allocation works for the coded case also. And as the EPRE ratio increases, SSRPA reduces the blocker rate more. So now that we have seen the analysis and mitigation of INA and ICI in CISO systems, now we'll focus on MIMO OFDM systems. So here the base station and the users are multi-antenna terminals. So the base station assigns a precoder and a power allocation to each user. Precoder gives the transmit directions for the MIMO layers, and the power allocation matrix is a diagonal matrix with positive entries. These powers give the powers of the each MIMO layer. The users use different numerologies, thereby they cause INI to each other. So now we are interested in computing the INI and ICI covariances for each user. So once again, it is sufficient to consider the two-user case for INI, and it can be easily generalized to the arbitrary number of users, as we have seen in the size of case. Later, we'll propose the optimal precoder and power allocation across MIMO layers. So here we'll assume all the subcarriers of a user are assigned same precoder and same power allocation matrix. So this is our system model. So at the base station, the signals for the two users using different numerologies are generated. So here, the information symbol vectors are denoted by S bar. The offset for subcarrier user 1 is O1. So these information symbol vectors are scaled by a power scale. So the square root of the power allocation matrix, and then they are pre-multiplied by the decoder. So which the output of this multiplication gives the pre-coded information symbol. So the covariance of this pre-coded information symbol vector is called the signal covariance, which is denoted by QK. The definition of signal covariance is shown here. So this can be computed as the product of three matrices. This is the precoder, power allocation matrix, and the Hermitian of the precoder. Now the transmitted signal from the base station is received at both users via their respective MIMO wireless channels. Once again, phase noise is induced by the RF modules at the receivers. And after the baseband processing, at each subcarrier, we get the estimates of the transmitted information symbol vectors. So these estimates contain desired signal component as well as INI and ICI components in addition to AWG noise. Now these INI and ICI components are vectors instead of scalars in the size of it. So we have to compute the covariances of these INI and ICI vectors at each subcarrier and for both the users. So here we are using the Wiener phase noise model as opposed to the filtered Gaussian process model for the size of these. Coming to the MIMO channel model, so we are using the Kronecker model. This is also called the separable product correlation model. Here, the MIMO channel matrix can be written as the product of three matrices. The first one is the square root of the received spatial correlation matrix, and the second one is the matrix with IID elements, and where each element is a complex normal random variable. The third matrix is the square root of the transfer spatial correlation matrix. So these spatial correlation matrices, they play a very important role in the analysis of MIMO systems, especially the eigenvalues, these correlation matrices. So for example, when the correlation matrix has equal eigenvalues, so we can say that the channel is uncorrelated because the correlation matrix will be a scalar multiple of identity matrix. Now, on the other hand, when there are only few strong eigenvalues and the rest of the eigenvalues are close to zero, we can say that the channel is highly correlated. Now, how do we compute these correlation matrices? These can be computed using the power angular spectrum. So the power angular spectrum gives the distribution of the received power as a function of the angular variable for the received case, whereas in the transmit case, it gives the distribution of the transmit power as a function of the angular departure. So here, the ijth element of the received spatial correlation matrix R can be computed using this expression, where SR of theta is the received power angle spectrum, and DR is the intra-antenna spacing, which is normalized by the wavelength. So a popular model for power angle spectrum is the Laplacian model, which is adopted by 3GPP. This is characterized by the mean and also a standard deviation for the angular variable. So this is our first result in the MIMO analysis, which gives the INI covariance at user 1. So here we are giving an expression for the INI covariance as a function of the subcarrier index and the signal covariance of the interfering. As we can see here, it depends on the received spatial correlation matrix of user 1, and it also depends on the matrix inner product between the signal covariance of interfering user and also the transmit spatial correlation of user. This scalar captures the effect of subcarrier location, the channel power delay profile, and also the phase noise bandwidth and the temporal autocorrelation. So here we use the expression for the INI covariance at user 2, once again as a function of the subcarrier index and the signal covariance of the interfering. Once again, we can see that it is proportional to the receive spatial correlation of user 2. It depends on the matrix inner product between the signal covariance of interfering user and the transmit spatial correlation of user 2. And from the scalar, we can see that it does not depend on the power delay profile of the channel, whereas the INA covariance at user 1 depended on the power delay profile of the channel. So here we show the expression for the ICI covariance at the user K. So once again, we can see that it's a scaled version of the receive spatial correlation of user K, and there is no dependence on the power delay profile. So now we validate our expressions which are derived for INI and ICI covariances using simulation. So this is our simulation setup. We have 3 users, user 1, user 2, and user 3. So user 1 uses 15 kHz subcarrier spacing, user 2 uses 30 kHz subcarrier spacing, and user 3 uses 60 kHz subcarrier spacing. So these are the offsets of the subcarriers to the users. So the offset of user 1 is 0, and the offset of user 2 is 7, and the offset of user 3 is 10. So these indices, when they are mapped to the lowest subcarrier spacing numerology, the mapped indices are shown in the bottom. So these are the parameters of the MIMO channel. So we are using the Laplacian power angle spectrum. The mean and standard deviation for the angle of departure for all the 3 users are shown here. And the mean of and standard deviation for the angle of arrival for the users are shown here. So in this plot, we are showing the normalized total INA power, which is summed across the antennas, the receive antennas, as a function of the subcarrier index for both the users. So, along with the total INA power, we are also showing the individual contribution of INA power from each interfering user. The subcarrier allocation is once again repeated here for reference. So as you can see here, the INA power has a wide dynamic range. And another key point to observe is that user 2 experiences higher INA power at both the edges, whereas user 1 experiences higher INA power only at the right edge. So this is because of the subcarrier allocation. So for user 1, all the interfering subcarriers are towards the right. So the rightmost subcarrier will get highest INA power, whereas for user 2, it is receiving INA from both the left edge as well as right edge. So both the left edge and right edge subcarriers, they have higher INA power. Another key point to observe is that the INA power at user 1 is oscillatory, and the individual contributions from user 2 and user 3 are oscillatory in nature at user 1. While at user 2, the contribution from user 1 is monotonic in nature, whereas the contribution from user 3 is oscillatory. So this is because the INA caused by a lower subcarrier spacing user is always monotonic, whereas the INA from the higher subcarrier spacing user is oscillatory. So in this plot, we show the result for the ICA power at each subcarrier of the users. So we are plotting the normalized total ICA power summed across the receive antennas as a function of the subcarrier index. As you can see from this plot, the dynamic range of ICA power is very small when compared to INA. You can see that user 2 has a lower ICA power when compared to user 1 because user 2 uses a higher subcarrier spacing. The plot for user 3 is not shown here, but the trends are similar. It has a lower ICA power because it uses the highest subcarrier spacing. So now, after seeing the analysis of INA and ICA, now we'll focus on the mitigation technique. So we'll be deriving the optimal precoder in the power allocation matrix for all the users. So first we'll focus on the precoder design. For designing the optimal precoder, we'll choose the objective function as the ergodic capacity of a user K, given the signal covariances of all the rest of the users. So the optimization variable here is the signal covariance of user K. So here we have a PhD constraint because our optimization variable is the covariance matrix. We have a trace constraint, which gives a upper limit on the total power. So the expression for the single user ergodic capacity is shown here. So notice the presence of ICI covariance and INI covariance. So because of these INI and ICI interferences, so the expression for the ergodic capacity is different from the conventional ergodic capacity expression. This has a special structure. Is a difference of two terms. So both of these terms are concave functions of the signal covariance. So this has a structure which is the difference of two concave functions. So this is your optimal precoder result for user K for any subcarrier. So given all the power allocation matrices of the users and the precoders of all the users excluding user K, the optimal precoder of user K is nothing but the eigenvector matrix of the transfer spatial correlation of user. So this can be proved easily. This is our proof methodology. So we'll expand the signal covariance of user K as a product of three matrices, ut of K, omega K, and the Hermitian of ut of K. So instead of optimizing over the signal covariance Qk, we'll be optimizing over omega K because ut of K is a unitary matrix. So whenever Qk is PhD, omega K is also PhD, and the trace of Qk and omega K are the same. So the constraint set remains the same. So iteratively, we'll null the diagonal elements of omega K and show that the ergodic capacity increases with each iteration. So finally, when the matrix omega K is diagonal, we show that the ergodic capacity is maximum. So that says that ut of K is the optimum precoder for user. We have used the techniques from Tullino and Lozano, but they have not incorporated INI and ICI in their analysis. So after designing the optimal precoders, now we are left with designing the optimal paths to the users. So for optimizing the power allocation, we'll choose the weighted sum rate as the objective function. So in cellular scenarios, weighted sum rate is a typical metric. So here, the weights for the users are different. Like, for example, a cell edge user will be assigned a higher weight, and a cell center user will be assigned a lower weight to ensure fairness. So the optimization variables are the power allocation matrices. Again, we have a total power constraint and also PhD constraint on the power allocation matrix. So this is a non-convex optimization problem. The objective function is non-convex. This we can solve using the SCA method, which is the successive convex approximation method. So in each iteration, the non-convex objective function will be replaced with a concave function, and iteratively this problem can be solved, and so the local maximum for this optimization problem can be achieved. Here we are plotting the weighted sum rate as a function of the scale Doppler spread. We are showing the results for two values of the phase noise bandwidth. The blue curve shows the results when the phase noise bandwidth is 100 Hz, and the red curve shows the results when phase noise bandwidth is 300 Hz. Here we are using our proposed power allocation method. The weights for users 1 and 3 are 0.4, and the weight for user 2 is 0.2. The ratio of the transmit power to the AWG noise variance is 20 dB. As you can see from the figure, that the weighted sum rate reduces, the increase in scale Doppler spread. Also, the increase in phase noise bandwidth, the weighted sum rate reduces drastically. So, Doppler spread and phase noise degrade the performance of the system. Here we are showing the effect of angular spread on the weighted sum rate. So we are plotting the weighted sum rate as a function of the standard deviation of the angle of departure for different MIMO configurations. And here we are also showing the impact of INI and ICI. The curve with INI and ICI is shown in the red color. The curve without INI and ICI is shown in the blue color. Here we can see that as the standard deviation for angle of departure increases, weighted sum rate increases for all the MIMO scenarios, because as the standard deviation increases, the channel becomes less correlated and the capacity increases. Now, one more point to observe here is that the impact of INI and ICI is severe for the higher order MIMO configurations, as there is a significant reduction in weighted sum rate with the presence of INI and ICI. Now we benchmark our proposed power allocation and recorder with the schemes available in the literature. So I'll explain the benchmarking scheme. So the first one is the DFT I square AP method, which uses a DFT recorder, and it is accounts for INI and ICI in designing the power allocation. This is shown by the pink curve, dotted curve. So the next one is the I square UPA method, which stands for INI and ICI unaware power allocation. This is shown by the black curve. It uses the same recorder as ours, but while designing the power allocation, it does not account for INI and ICI. The next method is the EPA, which is the equal power allocation method. It is shown by this red square marker. So it uses the same power allocation to all the MIMO layers. So thereby, the covariance matrix will be a scalar multiple of identity matrix, and the recorder is irrelevant here. The next method is the SVD based method, which is shown in this green color diamond marker. So this uses instantaneous channel to design the recorder, and also uses water filling method to design the power allocation. The last method is the strongest eigenmode method, which is shown in this brown marker. So this uses only the strongest eigenvector of the transverse spatial correlation matrix. So it will not use all the formulations. So as you can see from the figure, that the proposed method performs all the benchmarking schemes. And the strongest eigenmode method is the worst performer because it does not use all the MIMO layers. So now we'll compare the eigenmode power allocation of our proposed method as well as the I square UPA method, which does not account for ICI. So here, because our number of transmit antennas are 4, we have 4 eigenmodes. So here we are plotting the fractional power assigned to each eigenmode as a function of the normalized transmit power. The figure on the left shows the result for proposed method, and the figure on the right shows the result for I square UPA method. So as you can see here, the proposed power allocation method assigns higher power to the weaker eigenmodes, which are the eigenmodes 3 and 4, when the SNI transfer power is high. Whereas at lower transfer power, it assigns higher powers to the stronger eigenmodes, which are eigenmodes 1 and 2. On the other hand, when we consider I square UPA, it always assigns highest power to the strongest eigenmodes. And as the transfer power increases, power allocation approaches the equal power allocation, which is shown by this black horizontal line in the dashed curve. So these are our conclusions. So we have seen mixed numerology OFDM system. This is the key physical layer enhancement in 5G new radio. We have seen that they are affected by INA and ICI. We have analyzed INA and ICI by accounting for phase noise, time varying channel, power delay profile, partially occupied subcarrier, and wideband. We have analyzed SISO and MIMO systems, and we have seen that spatial correlation played a key role in MIMO. We have also proposed mitigation techniques for INA and ICI. In the SISO case, we have proposed power allocation across the subcarriers, and in the MIMO case, we have designed the optimal precoder and the power allocation across the statistical eigenmodes. So these are our journal publications, and these are our conference publications. So coming to the future works, so because OTFS is being considered actively for 6G, so the analysis of mixed-numerology OTFS systems will be an interesting idea for future research. Also, we have used the Kronecker model for
the analysis of my most modeling. A more general model like the Wieselberger model can be used to extend the results. So this will be another research idea. So the next one is the joint design of prequarters and correlations. In our work, we have separately designed the prequarters and the correlation to reduce complexity. Joint design of prequarters and correlations is another idea for future research. And also correlation algorithms with lower computational complexity. The co-design of transmit and receive architectures will be interesting ideas for future research. Thank you.